Hello. So today we move to numerical integration. So we'll study the approximations of integrals by the formulas which often called quadratures. So our intention is to compute. So we will be computing integrals. Like approximating integrals, so of some function on a given interval a, b. So let's give a name. So g of f, it will denote the integral of the function on a given interval. Approximated by the formula which is based on certain number of points. So it will be, the formula will have exactly the form b minus a. So this is size of the interval, and then we'll take a sum over m plus 1 points from 0 to m with certain with the values of the function. So integral is a limit of the sum, so we will approximate it by sum. So sum of the functions at certain points with certain coefficients. So the coefficients are called weights. So with weights alpha j, and the points where we compute the function, so it's nodal points xj. So essentially, we take function, it's a function of x, give some interval a and b where you want to compute it, so you have a function. And now we want to compute integrals, which we know is this signed area under the graph. And we do it by computing the function at certain points x0, x1, x2, etc. So we take certain points, which we will have to define, and take the values of the function at these points with some weights. And this should give us the approximation of the interval. So, of course, we cannot make it exact, so there is an arrow. The arrow we call E. F, it's a difference. So it's what's the difference between exact integral and approximated integral. Okay. So, usually our intention will be to give a formula which will approximate the integral accurately on short intervals. So if the interval is small, then the arrow should be small. So we want the arrow of the function or arrow of the integral should be of order h in some power j, where j should be bigger than 1, and h is the size of the interval. So h is the size of the interval, and we want that if the interval getting smaller and smaller, the error of approximation should have an order bigger than 1. So that's a setup that we want to have. Okay, so that's one piece of work, and it assumes that interval on which you approximate which you compute your integral is small. So what in the case when interval is large, so when the interval is large, then what you do is we'll do what's called composite integration. So what you do is what we do is we split the interval AB into small, into exactly how many use? We'll use n into n small subintervals of size h, which will be b minus a over n. So equal intervals. So what you do, if your interval is large, so you want to compute integral on this interval. So what you do, you split it into the pieces, smaller pieces, and then what we can do, if we can use this formula in each interval. So what we do is that we can use this quadrature at every subinterval. Right? So exactly what does it mean? It means that we define the points. So we define the size of the interval, and then subintervals will be a nu to a nu plus 1, where a nu is a plus nu h, and nu is 0, 1 to n minus 1. So we split the big interval to the smaller intervals, and then we can compute. So use quadrature in, so we will call it Q nu. So now in each interval we will use this formula that we're going to compute, to derive, in each interval. Subinterval. Okay. So in other words, what we do is that we compute the integral as a sum over all. Well, I don't like this new. Let's call it J. No, okay, it's okay. So over. So in each interval we have this formula. So that f is equal to q plus r plus e. So it will be the quadrature plus an arrow. Okay. So in numerical integration we forget an arrow. So this is approximately computed as with this formula. So in this case, what we can do is, what we can see is that, no, let's see. So what you do? So this is so you see each of these errors we will have as we'll have order j with the same formula that we're going to derive. So there will be, and there are n errors. So it's plus n times O. Size of the interval is now small h, subinterval in the power j. Okay? But now remember that this n is, see, it's b minus a over h, right? So this is OH minus 1. So that means that if you do it in this composite way, so that you can approximate the integral with this sum that can be computed. And then you just you have to subtract 1. This minus 1 is exactly why we, from the beginning, we asked that the order should be bigger than 1. So if the order is not bigger than 1, that it will not work in a composite way, the composite integration method. So essentially that's it. So if we have some specific formula for the quadrature, we know how to compute the integral, and if j is bigger than 1, then this will converge. So then so if j is bigger than 1, then this sum, if we forget for a while to round off errors, so then this sum converges to the exact interval as n goes to infinity. So given some formula for the quadrature, you just have to split your interval to more and more points, and then more points you get, closer you are to the value. So that's a very natural way. So what we will do, we will be deriving the formulas for this QV. So today we will do it in a general framework. So it will be Newton-Cote formulas. Which is a generalized way to how to see most of the formulas for integration that you probably saw before. So so how we will do so in this method. So there are two things. So you see, there are two steps here. So the composite integration means that we split it into the large interval into the small intervals, and computed the quadrature within each subinterval. Subinterval is small. So now each subinterval, in order to compute it by quadrature, we should still split more to m points. But m is now fixed. So here n capital was not fixed, so you split it more and more subintervals. But then after you split it within each interval, you still have m plus 1 points within each subinterval. So which is exactly this x1 to xm, x0 to xm. So now we have to define a nodal points inside subinterval, or we'll just call it interval. So we're back to the same notations, AB. So, but now AB, or if in other way it is subinterval. So, but we will not keep this index just to make it short. So, in the Newton-Cote formula, these points are now you're equally distributed. Equally spaced. So there are two ways how you equally space points in the interval, and the first way is will be open Newton-Cote formula. So open means that what you do is you take the interval between A and B and split it into m plus 1 points. It will be m plus 2 points, n plus 2 parts. N plus 2 equal parts, and start counting from not from the beginning, but from the next. And finish also not coming to the end. So all points are inside. So you split into equal subintervals, and open means that you all points are inside. So what you have, so the size of the interval is b minus a divided by m plus 2, so 2 plus m plus 2 intervals. And then each point will be a plus, the first point will be a plus h, so the next one. And the next, on xj, x0 plus jh, where j is from 0 to m. Okay, so this is open way, and obviously there is a closed version. As you can guess, so it's same idea. But now you divide it into the m intervals of the same size, and then you start counting from the end. So in this case, h subinterval size is b minus a over m, x0 is a, and xj is x0 plus jh, j from 0 to m. So the last point will be b. Okay. So the way how you derive this formula, I'll give it two ways. One way is convenient, has a little bit more general view, and the second way is more practical for computing coefficients. So there will be two derivations of this Newton-Cote formula. So derivation 1. So both derivations lead to the same answer. So the derivation 1 is done by requiring. So we require that our formula is exact. Yeah, so it's exact. R is 0. Is exact for polynomials, for all polynomials p of degree up to m. So for all polynomials with degree up to m, they should, our formula should be exact, and this should give us coefficients. So immediately, what we can see from here is that already before choosing coefficients, we can already see that. So what is the justification? So the justification is size of the arrow, and size of the arrow we can arrow estimate. Size of the arrow we can estimate directly from this property. So the error of the computation is a difference for arbitrary function. Is this difference? So now let's add and subtract JP. So first subtract, then add. But now all of this, and in the second time we can add Q because it gives the same value. So now both J, which is exact integral, and Q, which is quadrature, so both of them are linear functions. So are linear functionals. So this can be written as J F minus P plus Q P minus F, right? Okay. Just open up the formula. So the first will be the integral. And the second will be the sum. This sum. No, not this, of course. This sum. Okay. So now we can estimate this is smaller, modulus of this is smaller or equal than b minus a, which is size of the interval, times maximum of the function. And this can be also in a modulus approximated by some, let's just, without the sum. This can be approximated as small or equal to modulus of first times maximum of the difference. So this gives us the error of the computation in absolute value is smaller or equal than b minus a, and then it's 1 from the first, and then plus sum of absolute values of all coefficients. This is usually also 1. By the maximum of their difference. So you already see that it can work very, very well because this is size of the size of the integral. This is just normally constant, which normally we will have it equal to 2. And now this is for any, and this is true for any polynomial. Of degree smaller or equal than m. And we already know that in approximation theory that we actually, if the function f is smooth, we can very well approximate it by a polynomial. So the error will be small. So if f is smooth, we can make this difference very small. So this is already a promising way. So now let's do it exactly let's just do the job. So let's find alphas, and then let's directly approximate the error. So how to find alpha? Alpha j. And so essentially the question of existence and uniqueness, right? So let's solve the question whether the alphas exist and if they are unique. Okay, so since J and Q are both linear, so we have to verify these conditions. The condition was J of the polynomial is equal to Q of the polynomial. So since they're both linear, so we can only check it for polynomials, which is 1x, x squared until xm. So if it's true for every monomial, then it's true for any polynomial. Yeah. Okay. So we do this for the interval equal 0, 1. Of course, it can be done for any interval just by changing coordinates. So we just do it for interval between 0, 1. So what do we have? So for the we have to check this. So what this equation is written. So the left-hand side is just exact integral. So in the first case, it's integral by 1 dx from 0 to 1. On the right-hand side, it should be our formula. So a minus b is 1, so it's alpha 1, f, well, f is 1. No? So alpha 1 plus alpha 2 plus alpha m, alpha 0. So that's first equation. The second equation is with x. And here there will be the quadrature. And so on. The last is with xm. And you already see that this is a linear system of equations with respect to alpha, so it can be written as A alpha equal B. So here the A is a matrix of the following form. So it's 1 at the first row. The next row will be x0, x1, xm. And the last row will be x0m, x1m, xmm. So this is van der Monde matrix, so it's transposed van der Monde matrix. So we know it's non-singular. We know that van der Monde matrix is non-singular if all x's are different. So in our case, all x's are different. So then alpha is a vector of coefficients we wanted to derive, and b is this left vector, which are integrals, but these all integrals can be computed explicitly. So the first integral is 1, then this is 1/2, then 1/3. The last will be 1 over m plus 2 plus 1. Okay, so this proves that alpha exists and unique. So there is a unique way how to define all the coefficients. So in principle, this is one way how you compute the coefficients. Well, for example, let's consider closed method for m equal 3. So which means that x0 is 0, x1 is 1/3, x2 is 2/3, x3 is 1. And then you get the matrix which will be 1, 1, 1, 1. So it will be 0, 0, 0, 1/3, 9, 7. And it will be 1/3, 9, 3 by 2 by 2. No. Yeah, correct. 1, 1, 1. 0, 4, 3 equal to 1, 1/2, 1/3, 1/4. And this gives you the vector of alphas becomes, let's check. So it should be one, the answer should be this. So the first equation is that the sum should be 1, right? So always the sum is 1, which is correct. And the second equation is that this by 1/3 plus this by 2/3 plus this. Oh, you can check that. Should be correct. So that means that this formula estimates the integral of the function as a sum of 4 terms. So it will be one point at the end by 8 plus 3 by the point at 1/3 by 8. 3 point at 2/3 by 8 plus f at the end by 8. We have this function, and then split it into 3 intervals. And with these 3 points, we make a computation, but with special weights. So the weight at the point at the end, they are less important because they are given weight 1/8, and the point in the middle, they're more important. The weights are bigger. Okay, so that's it. So let's give another way of computing, and then we check what is the error of this approximation. Or better, after interval, but now what we discuss is that there will be topics that you want to present. In June. And there was we discussed that I forgot. We discussed that there are 2 of you want to have doctorate. No, 2, you and you. Right? Okay. So I have. So you take 2 topics, and then the others will take 1.
Yeah, last time you said that for doctorate students, we would do
2 half lectures.
Yeah, 40 minutes.
2 40 minutes presentation. So I do give you 2 different topics. And then the other will have just 1. And let's make it doctoral from master. I think it's fair.
The doctorate students will give a full class.
A full class, but I would prefer to have to give 2 different topics. So like
but it would take
1 hour and a half. Yeah.
Like for example, me in the Wednesday.
No, my idea was to give 2 topics such that 1 topic it will be 2 halves of the same topic. So then one day you give 1 half and you another half, and another day it's also 1 half.
Okay.
So let's see what I have. So for doctorate I have 2 ideas. Let's see if you like. So the first 2 topics, which are combined. So one will be chaos in Lyapunov exponents. So every question is a Syrian computation. So now that many systems has chaotic motion, so so essentially you don't need to give a full series, just idea. So what is the chaotic motion? It's closely linked to the existence of positive Lyapunov exponents. So what is the theory of this object mathematically, and how they usually compute it? You can also exemplify it on some classical example like Lorentz attractor. And then there is connected to this question is the question of fractal dimension. For example, fractal attractor, chaotic attractor. So the same theory and computation. So again, what is the definition of the fractal dimension? Or how they used for chaotic attractors, and how some overview how you can compute them numerically. So this is the first two that I would split between you, one to one, and then second, which I think both of you also will be useful. So is that parallel computing. General concepts and implementation in MATLAB. So, what is a parallel computing? So you have a multi-core system, many different processors. Essentially, good if you can prepare some overview. So, because there are different architectures. Sometimes you compute on multiple cores with shared memory. Sometimes it's not shared memory. And how it's implemented in MATLAB. Because MATLAB, or if you like some other language, it does matter. So usually this is extremely simple, in fact. So I want you to know it because it's actually the high-level implementation at MATLAB is very simple. So you just give several extra lines in your code, and it's just parallelized. So because MATLAB does all the job. But so that's a general view. And another is more specific, which is also useful probably for you, with another, is the same parallel computing on GPU. So this is GPU is actually the graphical card of your computer, and graphical card has the difference that graphical card itself has many processors, so many cores, many processing elements, and unlike the usual computer where you have just few very strong ones, the graphical card has a lot but very weak. So the difference is that in order to process an image, it's better, instead of having one strong processing unit, you have many weaker ones. And actually there is a way, and this gives a lot of gain when your problem can be parallelized to many processors, and you can do it on a graphical card. So now there are graphical cards which is GPU cards which are specially produced for numerics, and it's just the same concepts in MATLAB. And again, for MATLAB, the making this computational GPU on MATLAB, essentially it reduces to writing a couple of lines. Essentially, you just say, you compute all the rest on graphical cards, and then at certain moment you say, stop computing on graphical cards. So it's kind of trivial, but in order to make it efficiently, you need to know the concept, because otherwise it will not work. So, and often it can increase the speed of your computation by 10 or 100 times sometimes. So you just write extra 1 or 2 lines and you suddenly compute 100 times faster, just because it's different. Your code is well parallelized. So these are 4 topics which will be doctoral. And now I have more. So the more is the one who was for, there was somebody who was doing random numbers, the probability. There was some guy, he didn't come. So for him, I think what will be nice is that random number generation. Random and pseudo-random numbers generation. Okay. Because we often use random numbers. Computer there is a command that gives you random number, but this is not really true random number. So it's good to understand what it is and what is the idea behind this. What is the mathematical idea behind this? 6, what I think what is nice, and it's given in a book, by the way, but probably this book is not the best reference, is wavelet analysis, wavelet approximation. So it's another form of a basis, rather special form of the basis, which approximates the function, extremely used in applications. So, well, every smartphone uses wavelet approximation in many different ways. So it's just everywhere. So I didn't give you in the course, but it was in the book. So it would be nice if someone can take it. What else? Numbers. Okay, we need more, no? One. So master student, all of 3 of you want to have, you also want, no? So, we have 1, 6, 7. I didn't give you singular value decomposition, no? No. So this is good. Singular value decomposition. It was some initial part of linear algebra. So this is very important for some applications. Topic. Okay, so let's distribute what is here. So I suggest. So here the harder point is 2 and the harder point is 4. So maybe you take 1 and 4. 1 and 4, okay. And you take 2 and 3.
Yeah, that's what I was about to propose.
Yeah.
One from chaos theory.
Yeah, exactly. Yeah. So then you learn both, and then you combine. You may combine or whatever, but then one lecture you give 1 and 2, and another lecture you give 3 and 4. So then it will be more or less same topic, or whatever you like.
Okay.
So you take 1 and 4,
1 and 4, yeah.
and you take 2 and 3. Okay, no. So just look at the literature. If you will have troubles, I help.
Yeah.
But in general.
Yeah, I will need some help because I really don't know literature about parallel computer on GPU.
GPU, I can give you. We had a nice lecture by one of my ex-students about this, but what I don't remember if it was filmed. We have to check, and it was on his webpage. But when IMPA lost all this information, so the webpage also disappeared. So maybe we can just email to him and ask. And then, anyone likes something? Wavelet, good. So what's your name? Mars. Let's give names. So you? Carl. You? Serge. Anyone want SVD? Okay, so probably this I can give to that guy who is, unless you really want it, take it. So, and then I will think about some more topics, and then you decide. You can take SVD. Yeah. So what's your name?
Melvin.
Melvin. Convino. Okay, so for you, I have to think a little bit. Okay. So let's take a very, very brief coffee and then continue. So the second way leading to the same formulas is, so the first way was giving more conceptual view. So it's a formula which is exact on polynomials or up to a certain order. So the second way is just to give the polynomial, give exactly the best polynomial. So it turned out that you can just give, to say that the quadrature should be exact on special polynomial, and it will be the same as being the exact on any polynomial. So, well, no, what I'm telling you. So it turns out that you just ask for polynomial to be Lagrange polynomial. So we want to have that. So we require that I'm confusing the thing. So let's recall first. So what is Lagrange polynomial approximation? So Lagrange polynomial approximation is an approximation of the function by a polynomial with certain error, and polynomial is taken such that it passes exactly through the right points where you compute f. So f of at all points is exactly p at the same points, right? So that's a Lagrange polynomial is a polynomial which is exact at nodal points, and we know the formula for this polynomial. So it's sum over all nodal points of the function values, and then the coefficients are given by Lagrange polynomials of x. So this is exact formula, and so now what it is? So Lj of x, the formula is that it's product over all k which are not j, and then it will be x minus xk, xj minus xk. So it's a polynomial, if you remember, and then we also know the error. The error can be written as the derivative of order n plus 1 at certain point which depends on x. There is a factorial denominator, and then dependence on x is given by this product, which is x minus xj, so by this polynomial. Okay, so this zeta x is some point in the interval. So that's the theory that we had. So what we just do is we have a polynomial, and in order to compute approximation of the integral of the function, we compute integral of a polynomial. That's it. And we have approximation. And it turns out to be exactly the same as what we did before for arbitrary polynomial. So what you do is exact integral is it's integral from a to b and dx, and now f is equal to p plus r. Now we can substitute the exact form of P. It becomes sum J. This is a constant, so we can take it out of the integral, and what will be inside is in only Lagrange polynomial. Then dx. So this we call alpha j, and this we call E of f. And then it becomes exactly Q of f plus E of f as needed, right? So our weights are, so we have an explicit formula for the weights. These are integral of Lj of Lagrange function over the interval. So this is another way how to compute coefficients. Well, there is an example that I took from a book, but I'll just to have a some idea. So let's consider exactly the same example that we had before for 3 points, closed formula, so the closed version, and in this and interval, as before, we take 0, 1. Okay, so in this case, for example, the first coefficient alpha 0 will be the integral from 0 to 1 L0 of x dx. Now we know what is L0, so we take this formula. So we take we have to take a product of x minus, so excluding 0, so x minus x1, x minus x2, x minus x3, and divide by x0 minus x1, x0 minus x2, x0 minus x3, dx. So remember, so it's 3 points on the closed version, so it's x0 is 0, x1 is 1/3, x2 is 2/3, x3 is 1. Okay? And this you just integrate. So should be 1/8, etc. So the other four coefficients you can find in the same way, just integrating. So the important part of this theory is error. So how good is this approximation? Estimation. So we need to estimate this term E. And for this, it's convenient to use this version with Lagrange approximation, because we have direct formula for this R, this formula. So E of the arrow is the integral from A to B of this R dx. And now we take this formula and substitute. See? So it is integral in B fm plus 1 zeta x. Okay. Well, should be a little bit careful, but just assuming that it's integrable. So zeta x is chosen as its integral. Doesn't matter. So at the end, we can estimate the absolute value of the error by estimating each of the terms in this integral. So we can just take the largest value of the maximum of the m plus first derivative in the integral, so it's infinite norm, supreme norm, divide by this coefficient, which is also can be taken out of the integral, and then there will be this integral from a to b, and we can substitute difference by the modulus. Oh. Let's take the product. Dx. So next step is we change variables from x to z. So we take z to be x minus a divided by b minus a. So this is then when x is in the interval between a and b, automatically z goes to interval between 0 and 1. So we change the coordinate which maps a to b to 0 to 1. So this allows you to compute integrals. So that's the first term we keep. So what will we have? So we will have, so in that case, x is a plus b minus a z, and xj is a plus b minus a j zj. So when you take the difference, a will cancel, and there will be b minus a prefactor. So and they will come m plus 1 times because there is a product. So it will be b minus a m plus 1 for m plus 1 terms. And also there is dx, because when you change dx to dz, there will be one more b minus 1. So there will be in total m plus 2 prefactors when you change integration variable. And what will be, the rest will be integral from 0 to 1. Dz. Okay, so now this is already just a number. Right? So it does not depend on size of the interval, because it's size of the intervals which will be interesting for us. This is h. That's what we said we wanted. And then this is also the prefactor. So what we proved is that error is bounded by the prefactor, which is f. Well, let's write it so. We prove that error is h m plus 1, m plus 2, so this is the most important part, by some coefficient, which is, let's call it, this beta only depends on m, so it will be, we call it beta m plus 1, so m plus 1 terms. By beta m plus 1, by this norm, m plus 1. So we have this formula. So this means the order m plus 2. Oh, so whenever you have m points, you approximate the integral with the order m plus 2, which was our j, remember from the original formula. So So here we should give a very important observation. So when m is even, there are some extra cancellation occurs. So which gives you that actually the order of the method is actually higher, m plus 3. So for odd m, it's m plus 2, but for even m, it's plus 1, even plus 1. So that's why it's better to use even number of points than odd number of points. So this is a, you can see it exercise. It probably will be an exercise, but anyway, you can see it in the book. So now examples. So now we just what we do at the final part, we recover some of the typical ways how you compute integrals, just as particular cases of these formulas. So the first example, two examples. So the first example it's a trapezoidal rule. It corresponds to the formula for m equal 1 in a closed version. So in a closed means that the first point is A, and it's just one interval, so the last point is B directly. And then what you can compute is that there will be you will need two weights. The weights will be the same just by symmetry, because there is no. So it's fully symmetric situation. So weights should be the same, and you compute them as integral of the Lagrange polynomial. So take the first one, the x, and then AP. So this is the so what is the polynomial? Remember the formula. So it's x minus a, x minus x0 by x1 minus x1 minus x0. So this dx, and this is well, just compute it. So it will be b minus a over 2. This is b minus. Integral of this will be b minus a squared over 2, but then 1b minus a cancels. So which means that the way how you approximate the integral is b minus a over 2 half interval by sum of the functions. At the endpoints. And now let's see why it is trapezoidal rule. What this formula gives us? You have an interval AB. Function, so this is point A, point B. So the integral which is computed by this formula is the sum of the values by the half of the interval. So it's exactly the area which is given by trapezoidal rule. And whenever you use already the composite integration method, it means that you what you do is you split the large interval into equal smaller intervals. And then in each subinterval, you use this formula, which means that at each subinterval, you compute integral with the trapezoidal rule. So you approximate the integral in this way. And we know that the error of this approximation so m is even, so it should be m plus 2, 3. So it will be O of h cubed. Third order method. And in fact, you can give it exact form. So it's actually, so it can be, the coefficient can be estimated. So actually the coefficient is x cubed over 24 and by maximum of the second derivative. That trapezoidal method, everything works. So the next formula is m equal 2. Just do the same for m equal 2. And this will be, so it will be Simpson's rules. Simpson's rule. So it corresponds to m equal 2, closed. So this means that m equal 2, so this splitting of the integral into the 3 points. 3 points, and I will directly give you the final formula. Essentially, we need to compute weights. So weights you can compute yourself. So the result will be like this. So it will be integral divided by 6. And then it will be the first point plus 4 times the middle point plus the last endpoint. And then there is an error which you can the error can be estimated as h5 over 2880 by the maximum of the fourth derivative. Like this. So you see that you can make it very precise. So it's fifth order. Just for 3 points, you already have fifth order method for computing integral, very precise. So already take h is 0.001, and you already will have a machine precision, essentially. So, and out of 3 points, and the way important are weights. So the middle point should be taken with weight 4. So that's how it works. And then the open version. Midpoint rule. So midpoint rule corresponds to the m equals 0, open. So m equals 0 is no points at all. No points at all. No, 1 point. Yeah, because we start from 0. I'm getting tired. So open, and that's it. So essentially, so what it is, so there's interval a to b, and we just put 1 point in the middle. And this is the only way, the only point with which we estimate our integral. So the formula which will appear if you when you compute coefficients will be, so it's b minus a, f at this point. And the arrow can be estimated as h cube 24. You see, you just took 1 point and it's already very good, third order, because m is even. And what this formula means is just that we take this, we compute area of this rectangle that comes through this middle point. So the area is good because we put point in the middle. If we put it on the side, it will be already h2. And final is what's called 2-point open rule, which is obviously just the next version. So it's m equal 1 or open formulation. So what it is, it's we have the interval between a and b, and we now have to put 2 points inside. It will be x0, x1. So from these points, we approximate the integral, and then the final formula is b minus a over 2. So it'll be the first point, and symmetric, so the coefficients, of course, are the same. So x0 is a plus b minus a over 3. x1 is a plus 2/3 b minus a. So these 2 points, and then the arrow can be approximated as h cube over 38 second derivative maximum. Well, same order, somewhat better because coefficient is better, but with 2 points. That's it. You want to change mesh according to the second derivative. You mean?
Yeah.
Well, certainly, you see, certainly there are different adaptive methods. For example, if you know, but this is important. If you know that your problem is somewhat very stiff, it means that second derivative or thumb derivative is huge here and small in the rest of the domain, which sometimes is very important because sometimes you have, like you're computing singularity of some function, linear singularity, derivative goes to infinity. So you need to, then near the singularity, when the derivative is huge, so you know the error will be large, you can use smaller steps. In the other region, you use bigger steps. So this is quite often used method. So of course, this is it requires extra work because usually typical packages, they not always gives you this possibility, but this is a way, especially when you compute or stiff or directly when you study singularities, for example, and you will put smaller steps in the singularity, larger steps in the other region. And so this refers more to this composite way, because this composite, it doesn't have to be equally distributed intervals. You just use the same formula inside each, but these intervals can be different, of course.
That's what I was thinking about, because I think 2 weeks ago we saw the Chebyshev polynomials that optimizing the.
Optimized, but this we'll do next time, because this is another way. So there are, first of all, you can change sizes of these integrals in the composite integration in order to optimize with respect to second derivative. But there is also a way how to compute quadrature, because in quadrature, in this Newton-Cote method, we used equally distributed points. So now you can distribute points in a better way.
Okay, that's what
And that will be next. That we will see next time. That's it, no? We'll see it tomorrow.